Okay, today we're going to start our first set of notes on Unit 1 on momentum and impulse. We'll go through what those are and what they mean today and look at a few formulas and some examples. To begin with, just to get you thinking, let's ask ourselves, how does a karate guy chop through a cement block with his bare hands? Or why, when you fall on a trampoline, does it hurt less than when you fall on the floor? Or why do people in a big bus or semi don't get injured in a car accident compared to somebody in a small car? Those kind of questions. So a lot of those things are common sort of physics questions that we try to wonder why it works the way it does. And today we're going to figure out that the reason that happens basically is due to momentum. Momentum is sort of a weird topic. It doesn't really have a clear definition, something like velocity or distance or anything like that. It's sort of an idea that combines mass and velocity. So if you think of when we did Physics 20, we talked about inertia and kinetic energy. It's similar to those. So if you have something that's really massive, like a big, huge semi-truck, and it's moving at a fairly fast speed, it's going to have a lot of momentum. Where if we could have a little tiny car going at the same speed, but because it has less mass, it's going to have less momentum. So obviously the inertia plays a part. If something's at rest, it's going to want to stay there. If it's moving, it's going to want to keep moving. And also it has lots to do with kinetic energy, that if it has lots of energy, typically it's going to have lots of momentum. So we get this velocity and mass combination at play. What we find out, though, is momentum isn't really either mass or inertia or kinetic energy. So what we're going to do, let's kind of compare and contrast the two together. So the first thing you can see is when we compare momentum and kinetic energy, they both have mass, they both have velocity. The key difference, though, is kinetic energy. Remember, energy and work are similar, so kinetic energy means it has the ability to do work. Momentum can't do work. It just has its mass and velocity, and that's it. And when we compare it to inertia, if we have something that has a large or small amount of momentum, that's going to mean a high or large or small amount of inertia, whichever. So that's the big truck has lots of momentum, it's going to have lots of inertia. A little tiny object that's not moving very fast is going to have a little bit of momentum, it's going to have a little bit of inertia. And the biggest difference is inertia is just a definition or a concept. It's not something that we can actually measure with a formula. So our first formula that we're going to use when we're dealing with momentum is P equals mv. And P is the symbol we use for momentum. Not really sure why they chose P. I guess M was already used for mass and things like that, so they try to use a letter that's not going to be used, so we use P. And mass, our normal mass in kilograms, velocity, our normal speed in meters per second. And with momentum, when we multiply those two, we get kilograms times meters per second. So when you see here, the key thing to remember is momentum has no special derived unit. If you remember back to force, we said things were in newtons. So when we did energy, we said things were in joules. Those were all kilograms meters per second squared, kilograms meters squared per second squared. So we sort of made a derived unit named after somebody. Momentum doesn't. It's just momentum, and we go kilograms times meters per second. So let's do a couple of examples using that formula. So our first one, we have a 1,000 kilogram car moving at 10 kilometers per hour. So we just want to use P equals mv, so pretty basic. So we have 10,000 kilograms times velocity, but remember velocity has to be meters per second. So we have to divide 10 by 3.6, and that gives us 2.7 repeating. So the best way to do this on your calculator is type in 1,000 times 10 divided by 3.6, then you don't have to worry about rounding the decimals or anything like that. So we get an answer of 2777.7, and we'll round it to 2 sig digs because in our question, remember, we have 2 digits, so we'll round it to 2.8 times 10 to the 3 kilograms meters per second. Okay, so just like in Physics 20, we always want to don't round any decimals to the very end, and then round it correctly to the right number of significant digits. Okay, the next example I have on here is one we've sort of looked at before in Physics 20 as well. And this one is, we have a meteor. It's got a momentum of 1.13 times 10 to the 4. So e to the 4, remember, just means times 10 to the 4. So what's going to happen is it's going to slow down and it's going to lose its mass. So remember, when we do with these, we're still dealing with the same formula, but now our momentum number, whatever it was, that was 1.13 times 10 to the 4. Right? If we're going to go a quarter of the speed, that means we're going to have to times that amount by a quarter. And if we shrink the mass by 2/9, we're going to have to times it by 2/9 as well. So basically, we're just going to be taking our original momentum and timesing it by a quarter and then timesing it by 2/9. That's the easiest way to do these questions. So when we do that, we actually get a final answer of 627.7. So if we round it off, we want 3 digits, so we'll go 628 kilograms meters per second. Okay, so we did these kind of questions. Those of you who were in Physics 20, and if you can remember, we did things like, we double the mass, triple the distance, those kind of things. It's the same sort of idea, just using a different formula. Okay, our next definition for today is impulse. And impulse is basically just comparing what the change in momentum is. So if a car is stopped and it's going to speed up, it's going to have a momentum of 0 up to whatever its momentum is going to be when we have its mass times velocity. So momentum's changing, we call that impulse. So just a fancy word meaning change in momentum. But a couple of key things to be aware of here. So if impulse means momentum is changing, that means the object must be moving at different velocities. Right? So if the object's moving at a different velocity, we typically assume the mass stays the same. Right? If we're driving in a car, our mass of the car isn't going to change. All we're really doing then is changing our velocity. So what we do then is our formula then gets altered a little bit. So instead of just being P equals mv, we now have momentum changing. So we use the little delta sign for momentum, mass stays the same, and then our velocity changes to delta v. So remember a couple of key things. So remember, a change in momentum, or delta p, is going to be our impulse. And then delta v, just like we do before, that just means our final minus initial velocity. Okay, so let's try this next example. So we have a box of Tic Tacs, 15 grams, sliding along a table at 5, and Tom's going to reach down and slow it down, and then it's going to only be moving at 1.6. So the question is, what is the impulse? So if we use our new formula, our mass is 15 grams, so let's change that to kilograms, so 0.15. And our velocity, our change in velocity, will be from final minus the initial. So when you go 1.6 minus 5 times it by 0.15, that gives us a negative answer. So we get negative 0.051 kilograms meters per second. Okay, so because momentum is a change, we could be a positive answer, which means we're gaining momentum, or it could be a negative, which means we're losing. So impulse can be positive or negative. A couple of key things that we're going to link this to Newton a little bit. So if we're changing the velocity, that means that object has to be accelerating. Right? If our velocity is speeding up or slowing down, we're accelerating. And because acceleration can only occur if there's a force acting on it, right? We have to have force in order to get acceleration, so therefore force must be related to impulse. So because of this, good old Newton shows up once again, right? If we have a force involved, we have to have Newton's second law. And if you remember back in physics before, we used force equals mass times acceleration. That was sort of our key formula that we used. But if you remember on our formula sheet, we actually wrote it as acceleration equals force divided by mass. That was typically how we wrote it. But in reality, Newton didn't actually come up with that law or that formula first. He actually, his second law in original form was, he said that force is proportional to the change of momentum divided by time. So he basically said that as the momentum changes per second or whatever, that's how much force is going to be needed. So this is sort of how Newton's second law originated. And then what he did was, he said, well, we already know that for momentum, mass times velocity was our momentum. So if we go mass times velocity divided by time, but we also know that velocity divided by time is acceleration. So that's how we actually get force equals mass times acceleration. It's taking his original formula, momentum over time, and combining it with the new momentum formula, and that derives the force equals mass times acceleration. So what we're going to use then basically is both formulas. We have momentum equals mass times velocity. That's the one we used already. But now we're also going to use Newton's version of force equals momentum over t. But we're actually going to change them a little bit. So we're going to have momentum as mass times velocity. And let's change this one to be momentum equals force times time. Okay, and because they're both momentum, we can actually combine the two together. So we have mass times change in velocity. That was our impulse for that one. And now we see we have impulse for this one too. So that's also a force times a change in time. So we end up getting a whole new formula of combining these two. And this is on your formula sheet. And we can basically use this in any of three ways. If, let's suppose in a question I give you the mass, the velocity, and the time, and it's asking for the force, we can use this new formula to solve it for F. So you can solve it for any of the four as long as you have the three other ones. Or we might just use the left side to find impulse if we're given mass and velocity. Or we could use the right side to find impulse if we're giving force and time. So just depending on however the question's worded, you can sort of pick which part of the formula you want to use, all of it or just one of the two sides. They're all dealing with impulse, so that makes it a little bit handier to work with. So let's do this next example. We have a rifle shooting a bullet. So we got a mass, we got time, and we got a velocity. The question's asking, what is our force? So we're going to use this new combination formula and solve it for F. So our mass was 9 grams, so let's put that in kilograms, so 0.009. Our velocity, it started at 0 and it's leaving at 200. So we just have 200 minus 0. We can put that in if we want, or just leave it as 200, whichever. And then that'll be force times time. Same thing, our time took 3 times 10 to the negative 2 seconds. And it started at time 0. So we can put the zeros in if we want or not. It might be easier just to leave the minus zeros out. So now to solve it for force, just rearrange the equations. We'd have 0.009 times 200 divided by 3 times 10 to the negative 2. And that gives us an answer of 60 newtons. So we round it off to 3 sig digs. So we'll write it as 60.0 newtons. Okay, so just a quick example just to show you how you can use this new formula in combining both sides at once. So let's talk a little bit about momentum and force and all those kind of things just to sort of make sure you understand what's going on. So with our formula, so let's kind of deal with just looking at the force one. So our momentum formula, our impulse formula was force times change in time. So that means we could have a certain force and a certain momentum, a certain force and a certain time, and that would give us our answer of momentum. Okay, so let's just suppose we had a medium force and a medium amount of time. So now what would happen if we make the force bigger? So we use a large force, but then we use a smaller time. We can still get the same answer, right? So this is sort of like saying if our force was 5 and our time was 2, we'd have an impulse of 10. But now if we made our force 10 and our time 1, it's still 10. So we can have lots of force and a little bit of time to get the same answer. Or we could do the reverse. We could have a small little force and a huge amount of time. And that would also give us the same answer. So let's suppose our force was only 1, but now we're going to change our time to 10. We still get the same impulse. Right? Does that make sense? So because we're dealing with force and times, this goes into a lot of engineering to help us sort of deal with things like collisions. If we can increase one and decrease the other, then sometimes that'll help. Usually we can't change momentum, right? Because our mass is going to be the same, and our velocity, like if we're driving in a car and we're driving 100 kilometers per hour and we're going to come to a stop, our change in velocity is still going to be 100, our mass is still going to be whatever it is. So really the only thing we can sort of do is change the amount of force and time that act on the car. So this is, if you think in terms of collisions, this is why if you're driving a car, you'd rather hit a haystack as opposed to a brick wall. Right? We have the same mass, same velocity, but by hitting a brick wall, we're going to have a large force and a small time. So that's going to give us lots of force because we have lots of force over a small amount of time, right? So that's going to create the same momentum again, but lots of force. If we hit the haystack, then obviously the time's going to be bigger, so then we're going to have less force and a bigger time. So if we get a longer time period, then our impulse gets spread out, meaning our force then has to be smaller. So that's the whole idea behind airbags in a car, right? If we didn't have an airbag and we hammer on the brakes, we're going to have lots of force in a short amount of time when we hit the steering wheel. But if we have the airbag there, that airbag delays the time, so we get a longer time period, which then reduces the force. Remember, our momentum never changes. Our impulse is the same. Momentum and impulse mean the same thing again, so those aren't going to change. The only thing that we can sort of adjust is our time. If we make our time larger, our force will get smaller, which is a good thing. Okay? So that's why when we use a bungee cord, it's going to stretch out the time. We have less force. Or even if you fall on a wooden floor or a grass field or something like that, it doesn't hurt as much because the time, because that floor, the grass sort of bends a little bit, it sort of delays the time. Hurts a lot less than when we just fall directly on a concrete floor. So let's do one more example and then that'll be it for today. So here we have a 75 kilogram man. He's in a car accident. He's traveling at 65 kilometers per hour and he's going to come to a stop when he hits a truck. So part A is calculate how much force is on his body if he has no airbag and he just comes to a stop in a half a second. So we're going to use our new formula again. So force times time equals mass times velocity. So force is what we're looking for. Our time is 0.5 seconds. We have a 75 kilogram mass. And our change in velocity is from 65 to 0. But remember, we want to change 65 into meters per second. So let's divide that by 3.6. So we can do all of this all in one shot. So you'd have 75 times 65 divided by 3.6. And we're going to then divide it by 0.5. So when we do this, we get a force of 2708 newtons. And if we round it to 2 sig digs, that'd be 2.7 times 10 to the 3. Okay, so pretty big number. Okay, so now let's do the exact same question, but let's suppose the airbag now is just going to delay the time. So instead of going from half a second, it's going to go to 0.78 seconds. So we do the same calculation, except our time is 0.78. The rest of the question stays the same. Okay, so let's do this calculation, and we get an answer of 1736, or if we round that off, that'd be 1.7 times 10 to the 3 newtons. Okay, so if we compare these two forces, we can see that there's about 1,000 less newtons. Okay, so it might not sound like a lot, but maybe that's enough to keep the guy from being killed. So we could even kind of do a comparison. If we go 1.7 to the 3 divided by 2.7, you can see we get about 60%, 63% roughly. Okay, so quite a bit less force than when we have a shorter time. So with more time, So less force with larger time. Okay, a couple of key things to remember with this one, like technically our force we consider it being negative because our time, our speed was going from 65 to 0, so in our formula we'd actually have 0 minus 65, so that 65 would be negative, which would then make our answers negative, but obviously if we're coming to a stop, we have a negative force, right? We're accelerating in a negative amount. So really the positive negatives don't really make too much difference. And as I noticed this, if you were to compare this to the note page, they actually, there's a typo. In the notes I have it as 0.05 seconds, which actually would make the force 2.7 times 10 to the 4 without the airbag, which would obviously then be a lot bigger. So, but the calculations are the same. So that's it.